In chapter 10, we're going to talk about chemical bonding, basically part 2 of chemical bonding. And we're going to start off with talking about the VSEPR theory in sections 10.2 to 10.4. Okay, it stands for valence shell electron pair repulsion. And it's basically a theory that explains why molecules take on a particular shape or geometry that they do. Molecules strive to obtain symmetry and stability. Molecules will arrange themselves so that like charges are as far apart as possible. Like charges with the same valence shell electrons repel. Okay? The geometry or the shape of the molecule depends upon the number of atoms bonded to the central atom, so the bonding electrons, the number of atoms bonded to the central atom, and if there are any lone pairs or non-bonding electrons existing on the central atom. So molecules will take on a shape depending upon the central atom and what is bonded to the central atom and any lone electron pairs on the central atom. In order to determine what molecular geometry a molecule has, we need to draw its correct Lewis structure first, and then look at that central atom and look at how many atoms are bonded to it and look at how many lone pairs, if any, are on that central atom. We're going to talk about 11 possible shapes. Now I know in Chem 110 only 5 are primarily discussed. We're going to talk about 11 possible shapes because now we've taken into account more exceptions to the octet rule in drawing Lewis structures. So we're going to look at 11 structures and look at examples of 11 shapes. Okay? I'm going to list the 11 shapes and some information about them, which is similar to figure 10.1 in your textbook. And then I'm going to go through later on in this video and show you 3D models of each of the shapes. To determine what shape a molecule has, we must draw the correct Lewis structure. Once you have the correct Lewis structure drawn, you want to look at the central atom of that Lewis structure and how many atoms are bonded to it. Look if there are lone pairs on the central atom. Okay, everything's in reference to the central atom. We don't care if the adjacent atoms have lone pairs. That does not determine that's not a determining factor in the overall shape of the molecule. Using that information, atoms bonded to the central atom, lone pairs on the central atom, we can use table 10.1 in our textbook, which I'm going to show in a little bit in this video, or the table below, which I've started and I'm going to continue, to determine the molecular geometry or shape according to VSEPR theory. Okay. I'm going to summarize table 10.1 a little bit differently. It's the same information, I just want to present it in a different manner. Okay? When you have two atoms bonded to the central atom, you have two possible shapes that could result. You can have a linear shape or a bent shape. Two atoms bonded to the central atom and you have no lone pairs on the central atom, you have a linear structure. And an example would be carbon dioxide. Okay, you have your central atom, which is carbon. You have two atoms bonded to the central atom, no lone pairs on it. It gives it a linear structure. A bent molecule, you have two atoms bonded to the central atom, but on that central atom you can have one or two lone pairs. That affects the shape of the molecule because now you have these lone pairs on that central atom pulling it away from the plane of the two hydrogen atoms which are identical. So water is a perfect example of a bent molecule. In contrast to carbon dioxide, you see these two carbons, they're identical. Okay, they want to be as far apart from one another as they can be. Okay, valence shell electron pair repulsion. Like atoms, likely charged atoms, similar charged atoms or identical, want to be as far apart from one another as can be. But when you have a bent molecule, you still have those like atoms as far apart as can be, but because you now have lone pairs on there, you have those negative electrons on that central atom pulling it away. Okay? So I'm going to go through and I'm going to show you several other shapes And then you're going to see actual 3D models where I go through an example of what it looks like with ball and stick figures or three-dimensional models. Let's look at when we have 3 bonded atoms to the central atom and 4 bonded atoms to the central atom. If we have 3 atoms bonded to the central atom, we have 3 possible shapes. Trigonal planar, we have 3 atoms bonded to the central atom and no lone pairs on the central atom. And an example would be boron trifluoride. Boron does not follow the octet rule. It has less than 8 electrons around it when it is in a neutral molecule bond. So you have a flat molecule. And you're going to see when I go through each one with 3D models. I don't have enough space on the board, so I did this a little differently. Trigonal pyramid, 3 atoms bonded to the central atom, and then you have 1 lone pair on the central atom. So basically on this nitrogen atom, you would have a lone pair that would pull the nitrogen above the plane of the 3 hydrogens. In contrast to trigonal planar, where it would look like a triangle, a flat triangle. The boron in the center, and the 3 points of the triangle being the fluorine atoms. T-shaped, 3 atoms bonded to the central atom and lone pairs, 2 lone pairs on the central atom. It gives a figure like a T. And an example of that would be chlorine trifluoride. And you'll see when I go through with the 3D models for each one, you'll see. What if we have 4 atoms bonded to the central atom? We can have 3 possibilities. Tetrahedral, which you're probably familiar with from prior chemistry, and then the distorted tetrahedral, usually called the seesaw, and square planar. You have 4 atoms bonded to the central atom and no lone pairs. That gives you a tetrahedral structure. It looks like a pyramid with an antenna sticking out at the top of the pyramid. And things like methane, carbon tetrachloride, those molecules would have a tetrahedral structure. No lone pairs on that central atom. That central atom is bonded to 4 other atoms and it has no lone pairs on it. But we learned about octet rule exceptions. Okay. The next set of shapes after tetrahedral are for molecules that go over the octet, that have expanded octets. So the seesaw distorted tetrahedral shape, you have 4 atoms bonded to the central atom, but then you have 1 lone pair on the central atom. So for this example here, sulfur tetrafluoride, on top of the sulfur, you have 1 lone pair that is not in a bond. So you have sulfur bonding to 4 halogens, but on top of that sulfur, you have a lone pair, and it gives the molecule a seesaw structure, which you'll see when I do the 3D models following this chart. Square planar, you have 4 atoms bonded to the central atom, kind of like the corners of a square, and the central atom is in the middle. And then if you look at that square, okay, picture this, I know it's a rectangle, but pretend it's a square. And on top and underneath the square, you have lone pairs that exist above and below, which we would say axial and inaxial positions. Okay, so we have an example, xenon tetrafluoride, and you say, well, xenon, I thought that's a noble gas. It actually bonds, it reacts. This is extreme conditions. This is not under natural conditions that you can get xenon to bond. Okay, so these are examples of when you have 3 bonded atoms to the central atom and 4 bonded atoms to the central atom. What if we have 5 atoms bonded to the central atom, or 6? Because remember, when we talked about the octet rule exceptions, we said that sulfur can have up to 12 electrons around it. So we have a molecular geometry to fit that octet rule exception. So let's continue on with when we have 5 bonded atoms and 6 bonded atoms. The last 3 shapes we're going to go through, again, represent molecules that have an expanded octet. Trigonal, bipyramidal, and square pyramidal represent molecules that have 5 bonded atoms to the central atom and either 0 or 1 lone pair. Trigonal, bipyramidal, 5 atoms bonded to the central atom, no lone pairs. So an example, phosphorus, when it bonds with a halogen, we said it can have it can expand to 10 electrons. So it has an expanded octet. So the 5 bonded atoms to the phosphorus, no lone pairs, would give you a trigonal bipyramidal shape or geometry. If you have 5 atoms bonded to the central atom and you have a lone pair on it, that's going to affect the shape and make it a square pyramidal shape. So it'll look like a pyramid with 4 bases, and you'll have 1 central atom here coming up because that lone pair on that central atom pulling it above the plane. And then you'll have your other atoms bonded to that. Okay? Octahedral, when you have 6 bonded atoms, so for example, sulfur exceeding the octet rule and having 12 electrons around it, or 6 bonded atoms around it, no lone pairs, would have an octahedral structure. It's an example of an octahedral structure just drawn here, and you're going to see following right after this, you're going to see the models for each of these shapes that I have written on the board and that are referenced in figure 10.1. But I want to point out now, so here this would be a 2-dimensional representation for an octahedral molecule. Okay, and it's flat. It's drawn on a board. But in reality, it's not flat. You have your central atom designated in blue. You have 4 bonded atoms in a square-like position, okay? And then you have above that square and below that square another atom above and below. The atoms that are in the same plane, the 4 atoms that are in the same plane, we call the equatorial positions, like the equator, okay? Think of a globe, the Earth, okay? The equator. They're surrounding the core, the central atom. And then you have above and below the other 2 remaining atoms. Or it can be electron groups too, the lone pairs. And they are at axial positions, like the North and South Pole. Okay? So when you have these larger shapes going beyond tetrahedral, you have this kind of geometry to visualize. Molecular geometry is not calculation math. It's geometry. So you're working that part of your brain, that spatial part of your brain, that visualization part of your brain, which is very important for organic chemistry. Because in organic chemistry, we're looking at how things are going to react, their shapes, their reactivity. So it's working that part of your brain. Now let's look at a 3-dimensional example for each of the shapes listed in figure 10.1. Okay, here's, table 10.1. Okay, and table 10.1 I summarized with these, with this board as well. Okay, I just presented it a little bit differently. So let's see the 3D models, the ball and stick figures. I'm going to go through some of the molecular geometries that are mentioned here in table 2.1. I'm going to go through and show you a 3D model of 11 molecular geometries. Linear. A linear molecule has 2 bonded atoms and 0 lone pairs on the central atom. An example of a linear molecule would be carbon dioxide. A linear molecule has a bond angle of 180 degrees. If I take this protractor here and I align the central atom as the vertex of the angle, okay, we have a 180 degree bond angle straight across. A bent molecule has 2 atoms bonded to the central atom, but now you have lone pairs on the central atom, which change the geometry of the molecule. You have the lone pairs on the central atom that are pulling the central atom away from the adjacent atoms and bending it. An example of a bent molecule would be the water molecule. If we look at the bond angle of a bent molecule, we have roughly, it's actually 109.5 degrees, but you can see here from the protractor, you line the central angle at the vertex of the angle, and you see that it's right around 110, okay? A little bit shy of it, close enough, okay? So when you have two adjacent atoms bonded to the central atom, you either have a linear geometry, linear, or you have a bent geometry. Well, what if we have three bonded atoms to the central atom? Trigonal planar. Okay, trigonal planar molecule is a flat molecule, three bonded atoms, no lone pairs on the central, it's flat. Okay, an example of this molecule would be boron trifluoride. Okay, boron is an exception to the octet rule, so you only have 6 electrons around the central atom. Okay, it's a flat molecule. If we were to take the bond angle of a trigonal planar structure, okay, we have roughly 120 degree bond angle. You can see aligned here with the protractor. Well, if we have 3 atoms bonded to the central atom, and then let's say that we have lone pairs now on the central atom, that's going to change the geometry of the structure. Okay, valence shell electron pair repulsion, you have like charges repelling each other. If you have lone pairs on the central atom, you're no longer going to have a flat molecule. You have a pyramid, trigonal pyramid. So you see how it is above the plane of the flat surface. An example of a molecule that is a trigonal pyramid molecule would be the ammonia molecule. If we were to take the bond angle, okay, of a trigonal pyramid structure, okay, align the vertex. There we go. Sorry, get that there. Okay, it's a 109.5 degree bond angle. If you can see here from the protractor, it's right at about 110 there. Okay. So trigonal pyramid structure, if you have one lone pair on the central atom. Now, what if you have 2 lone pairs on the central atom and 3 atoms bonded to it? This is a new shape that we don't discuss in Chem 110, but in Chem 121, we have the T-shaped molecule. Okay. So T-shaped molecule is a very strained molecule here, and we would have 2 lone pairs on this molecule. Bond angle roughly about 90 degree. You can see that right there. Okay. And an example of a molecule that would have a T-shaped structure, let me put that way, would be chlorine trifluoride. A very strange structure. It doesn't really occur as frequently. So the 3 bonded atom groups, we have the trigonal planar with no lone pairs. We have the trigonal pyramid with 1 lone pair. And we have the T-shaped with 2 lone pairs. Okay, so they are the 3 bonded atom groups. What if we have 4 atoms bonded to the central atom? 4 atoms bonded to the central atom would give us tetrahedral. Okay, no lone pairs on that central atom. If we were to take the bond angle, again, we'd have roughly 109 degree bond angle. Let me try to show it here. Okay. All right. So no lone pairs on the central atom. A molecule that would have a tetrahedral geometry would be methane, carbon tetrachloride. Okay, no lone pairs. And in Chem 110, we kind of stop at that structure right there. But we're in Chem 121 now. We're going to go beyond that. What if we have 4 atoms bonded to the central atom And now we have lone pairs, okay? These are octet rule exceptions. These are examples of molecules that exceed the octet. Well, then we would have something called the seesaw structure, or the distorted tetrahedral. It's like a seesaw. Seesaw. Okay. So the seesaw molecular geometry, you have 4 atoms bonded to the central atom, okay? And you have lone pairs on the top there, okay? So something like sulfur tetrafluoride would have this structure, okay? And the lone pair, would be sitting there on the top, okay? And it's a distorted structure. It's a strange structure. Again, this is when you exceed the octet rule, the type of structures that you get. Another structure, 4 atoms bonded to the central atom, but now 2 lone pairs. You have this square planar structure, okay? So if you look at that, square planar, it's flat, okay? It's meant to look like a square. I know it looks more like a rectangle, but it's meant to look like a square. And you would have the 2 lone pairs, one on top and one underneath of the molecule. Okay, that's where the 2 lone pairs would go. This is a square planar. Okay, so when you have 4 atoms bonded to the central atom, you can have either a tetrahedral structure, you can have a seesaw structure or distorted tetrahedral. I like the seesaw name better because it's much more realistic. And then you have the square planar structure, okay? So these are when you have 4 atoms bonded to the central atom, no lone pairs on central, 1 lone pair on central, 2 lone pairs on central. Okay. Well, what if we have a molecule that has 5 bonded atoms? Okay, so again, this is exceeding the octet rule here. We have trigonal bipyramidal structure. Okay. Let me hold it that way. Okay. Get that one out of the way, sorry. Okay. So we have 5 atoms bonded to the central atom and no lone pairs on this structure. Okay. So if you look at it the way I'm holding it, okay. I'm holding it this way. There you go. Okay. So you have the triangle there, okay? And then behind the triangle, you have 1 atom, and then sitting on top there, you have the 5th, okay? Trigonal bipyramidal. And an example of a molecule that would have this structure would be phosphorus pentachloride, okay? One of the examples that I mentioned when I discussed exceeding the octet rule. Okay, phosphorus can have 10 electrons around itself and 5 bonds. And this is an example of what that molecule would look like when that occurs. Okay. Well, you can also have a molecule where you have 5 atoms bonded to the central atom. And then you can have a lone pair. And that would give you a square pyramidal structure. Square pyramidal structure right here. Okay. So if you look, it looks like the square. Okay. Even if it may look a little more like a rectangle, it's meant to look like a square. And then you have the 5th atom. Okay. Sitting there on the other side of the square. And then your lone pair electrons would go here on the other side. Okay. So square pyramidal structure, something like a bromine pentafluoride structure. Okay, again, these are exceeding the octet rule exceptions in some of the structures that you can have, the geometries you can have when this occurs. Okay, so when you have 5 bonded atoms to the central atom, your possibilities are trigonal bipyramidal and square pyramidal. Okay, and again, all these structures that I'm mentioning are in table 10.1 of your textbook. I'm just showing you 3D models of them. Your book has nice pictures and a nice chart, but let's visualize what these look like. We need to see examples, models. Okay, last but not least, if you have 6 atoms bonded to the central atom. Remember, we talked about sulfur having this capability where it has an expanded octet where it can fit 12 electrons around itself. You have this octahedral geometry, okay? So you have, no matter which way you look at it, okay? So you have octahedral, okay? 6 atoms bonded to the central atom, no lone pairs on the structure. All right, and this would be sulfur hexafluoride. Okay. In these octet rule exceptions that I had mentioned, the models especially seesaw, square planar, trigonal bipyramidal, square pyramidal, and octahedral, those bond angles are roughly 90 degrees. It's the distortion of the, it's a packed-in molecule. So we can see here, if I put it back to the protractor, okay, roughly 90 degrees. If we look at the square pyramidal, okay, again, 90 degrees. Trigonal bipyramidal, again, 90 degrees. Square planar, okay, it's supposed to be 90 degrees, but my model, I had to fix that. And seesaw, okay, 90 degrees, okay? So again, what I went through this chart right here, okay? And showed you in an example of each of these molecular geometries listed here. Okay, you can see here in the textbook, okay, you have the actual Lewis structure drawn for a representative example, and then you have a model here drawn, okay, in the textbook, but I showed you the real 3D models to help visualize it a little bit better. Molecular shape and polarity. We talked about polar and nonpolar covalent bonds in a previous video. Now we're going to look at molecules overall, covalent molecules overall, to determine if that molecule as a whole is polar or nonpolar. Polar molecules are molecules that are asymmetrical, not symmetrical, having an unequal distribution of charge. You have an overall dipole moment. The book talks about a vector addition, which is kind of a physics term, but I'm going to explain it a little bit differently here. Certain shapes tend to have molecules that are polar. Okay, there's always some exceptions, but in general, shapes that have lone pairs on the central atom usually give polar molecules. Let's look at 2 examples of polar molecules, water and ammonia. Water, H2O, Lewis structure. Okay, you have a bent shape for the water molecule. You have lone pairs on the central atom of oxygen, and those lone pairs on the oxygen pull the oxygen away from the plane of the 2 hydrogens. Now remember, in a previous video we talked about dipole moments, we talked about partial positive charge, partial negative charge. Okay, so the hydrogens are more positive and the oxygen is more negative. If you look at electronegativity values, oxygen is much more electronegative than hydrogen. So you have here this arrow with the plus at the end where you have the more positive molecule, more positive atom, and the tip of the arrow is pointing towards the atom that is more electronegative. So you have these 2 dipoles which do not cancel out. They're not going in opposite directions. They're going together. So they're adding together. You could look at it that way, okay? Or you could look at it as symmetrical versus asymmetrical. And everybody, may understand it a little bit differently. Some of you, the vector addition may just make sense, but some of you this way may make more sense as well. Okay? If I draw a plane through this molecule, this side is different than that. Okay? You have a negative side here and you have a more positive side here. That's asymmetrical. You say, okay, well what if I did it like that? Then it's exactly the same on both sides. But you can do it this way and it's not. So if you view the molecule with the plane going through right there, one side is more negative and one side is more positive, asymmetrical distribution of charge, unequal distribution of charge, polar molecule. Okay? And because water has a bent shape and is a polar molecule, it makes it do so many different things when it comes to what it does with solutions and so forth. Okay, I don't want to get off track. All right, ammonia, NH3, has a trigonal pyramid structure. You have nitrogen as your central atom, 3 hydrogens bonded to that central atom. The nitrogen is more negative, has a partial negative charge, than the hydrogens, which are more positive. So you have 3 dipoles, okay, all going together, all right, adding together. So you don't have any cancellation of dipoles. They're all going in the same direction. It's not like one goes one way and the other goes the other way to cancel out. If you look at this molecule, one side of it, the top, if you're viewing it this way, as depicted, is more negative, and this side is more positive. Again, asymmetrical distribution of charge. Okay? Table 10.2 also has some helpful hints. Kind of going here, certain shapes tend to give polar molecules because of the presence of lone pairs on the central atom, pulling it away from the plane of the other atoms. But there can be exceptions. We're not going to get too worried about them. But polar molecules, asymmetrical, unequal distribution of charge. Well, what if we have a molecule that is nonpolar? What does that mean? Nonpolar molecules are symmetrical. They have an equal distribution of charge. The bond dipoles cancel out, therefore leading it to be symmetrical and have an equal distribution of charge. Typically, shapes that have no lone pairs on the central atom tend to give nonpolar molecules. There are some exceptions. We're not going to worry about them. But let's look at 2 examples of nonpolar molecules. Silicon dioxide, also carbon dioxide too, would have a linear structure. Okay? The silicon would be slightly positive in comparison to the oxygens if you look at electronegativity values. So your bond dipoles are going in opposite directions, they cancel out. If you like the symmetry, symmetrical versus asymmetrical view, this way it's exactly the same, this way it's exactly the same. Equal distribution of charge on all sides of the molecules, nonpolar molecule. If we look over here, carbon tetrachloride. The carbon is more positive, partial positive charge in comparison to the chlorines, which have partial negative charge. Chlorine is more electronegative than carbon. If we look at the dipoles, okay, we have positive going to negative, and we have 4 of them. Okay, they are canceling each other out. The molecule is symmetrical no matter which view you look at. Okay, it's symmetrical on both sides or wherever you put that imaginary plane. Nonpolar molecule. Table 10.2 is good to go over. The book is pretty heavily on explaining with vector addition, with the dipole moments. If you like that explanation and that works for you for understanding it, that's great. If the symmetrical versus asymmetrical way works for you better, depending on how you visualize it, that's all that matters, okay? As long as you can distinguish between polar and nonpolar molecules. The next video will focus more on valence electrons and bonding, and we will get into some other theories on bonding, valence bond theory, molecular orbital theory, and hybridization of orbitals in subsequent videos.